Hello everyone, this is Dr. Tasuduk Hussain, and today's lecture will be dealing with the wave mechanical concept of atom. Some of the lectures that we previously discussed were dealing with the quantum mechanical concept of atom, and now we will have some lectures about the wave mechanical concept of atom. Some of the major contributions that were made in wave mechanical concept of atom were by Louis de Broglie, Heisenberg and Schrödinger. Now all these contributions made by these scientists will be divided into three different lectures. So today's lecture will be dealing with the de Broglie's concept or wave mechanical concept of atom. So this lecture is divided into 5 different subparts. So first we'll go through the introduction part of the de Broglie's concept. Then we will look at how the equation of a wave mechanical concept of atom is derived. Thirdly, we will look at how the de Broglie's wave equation can be experimentally verified. That is, we have to verify both the wave nature and the particle nature experimentally. Fourthly, we will see how de Broglie's equation can be applied to the conformation of a Bohr's quantization of angular momentum. And lastly, we will look at the significance or some of the limitations that de Broglie's concept has, and we will wrap up the lecture with that. Now let's move towards the introduction part. So in order to develop a more suitable and general model for atom after Bohr's model that was proposed in 1913, 10 years later in 1923, the dual behavior of matter contributed to the formation of such a model. Okay, now the French physicist Louis de Broglie in 1923 proposed that matter like radiation should also exhibit dual behavior. So matter should also exhibit dual behavior in a similar manner as light has dual behavior. This idea was based on a fact that nature always loves symmetry. Nature loves symmetry. Now, since before de Broglie's concept, we knew that light has a dual behavior. So de Broglie introduced a concept wherein he said that matter should also have a dual behavior. This means that as the photon has momentum as well as the wavelength, the photon, light contains of photons, as the photon has particle nature and it also has wave nature, in a similar manner matter should also have particle nature and it should also have wave nature. In other words, I can say that the electrons should have a momentum as well as a wavelength. Electrons should also have momentum as well as wavelength. Einstein in 1905 suggested that light shows the dual behavior. This concept was shown by Einstein in 1905. Light behaves both as the material particle as well as the wave particle, and de Broglie extended this Einstein's view and said that all forms of matter like electrons, protons, neutrons, or molecules or atoms should all also show the dual character. He further said that the wavelength, that is the wavelength lambda of any moving particle which has a mass m and a velocity v should always be given by the equation h by mv, where h is the Planck's constant. This equation is called as the de Broglie's wave equation and lambda is called as the de Broglie's wavelength. So this is de Broglie's wavelength and the whole equation is called as the de Broglie's wave equation. The de Broglie relation implies that the wavelength of a particle should decrease as its velocity increases. That clearly indicates that lambda is inversely proportional to the velocity. As the velocity increases, the wavelength associated with the particle decreases, and vice versa. It also implies that every object in motion has a wave character. The wavelengths associated with the heavier particles are so short that they can't be measured, while as the wavelengths that are associated with the subatomic particles like electrons or any other lighter particles can be detected by doing some of the experiment. The waves associated with the particles in motion, they are always called as the matter waves or de Broglie waves. So in case of matter, the waves that are associated with the matter are called as the matter waves, or you can call them as de Broglie waves. These waves differ from the electromagnetic waves as they have lower velocities and have no electrical and magnetic field, and also they aren't emitted by the particle under consideration. In the right hand corner, I'll be showing one of the images where you can see that the electromagnetic waves have the electric field as well as the magnetic field, while as in case of matter waves, the particles that are in motion, they don't have, they have kind of lower velocities associated with them, and they have no electrical or magnetic field associated with them. Now moving to the second part of our lecture, where we will be deriving the de Broglie's wave equation. So de Broglie's wave equation or wave relation is derived with the help of Planck's quantum theory and Einstein's equation. So these two will be used to derive the de Broglie relation. So how we will do it is, we know according to Max Planck of quantum theory of radiation that the energy that is associated with a photon is always equal to h nu, where nu is the frequency and h is the Planck's constant. Now since we know that this nu is always equal to c by lambda, we can put this equation as E is equal to hc by lambda, and we'll call this as equation first. According to Einstein's equation, we will say that E is equal to mc square. In other words, we say that mass slowly changes to energy when light falls on it. So mass slowly changes to energy when light falls on it. So this is Einstein's equation. E is equal to mc square, and we will call this equation as equation second. In this case, m is the mass of the photon and c is the velocity of light. When we compare these two equations, equation first and equation second, we see that the left hand sides are equal. That clearly indicates that the right hand sides are equal. So that means that hc by lambda is equal to mc square, or in other words, we can say that mc square is equal to h nu. So now if I see that here is one c, there is one c, they will cut each other, and then the equation becomes from here h by lambda is equal to mc, or in other words, we can say that this lambda is equal to h by mc. Okay, so this equation is lambda is equal to h by mc. Now suppose if we say that the velocity of a moving particle is v. Okay, so we'll replace this c with v. So when I say that the velocity of a moving particle is equal to c, that is the velocity of a light, then in that case what we can do is we'll say that lambda is again equal to h by m v, or lambda is equal to h by p, because mass into velocity is always equal to p, which is momentum. Again, since h is a constant, we can put in a proportionality sign. We can say that lambda is inversely proportional to the momentum. So that means the wavelength is always inversely proportional to the momentum. Or in simpler terms, if we simplify it, we can say that the wave nature is inversely proportional to the particle nature. That the wave nature is inversely proportional to the particle nature. So this becomes the de Broglie's derivation for the wave mechanical concept of an atom. This de Broglie relation, it implies that the wavelength of a particle should decrease as its velocity increases. It also implies that every object in motion has a wave character. The wavelengths associated with the heavier particles are so short or so small that they can't be measured, whereas the wavelengths that are associated with the electrons and other lighter particles can be detected by doing some of the experiments. So that takes us to the next part of our lecture, wherein we will study the experimental verifications of the de Broglie's wave mechanical concept, because herein we are saying that the matter has a wave nature and the matter has a particle nature. So both of these parts will be discussed in the next section. In the third part, where we are studying the experimental verification of the de Broglie wave equation, we will divide this section into two parts, wherein we will be experimentally proving that the matter has wave nature, and then experimentally we'll be showing that matter has particle nature also. But before doing that, we should know that how de Broglie's equation can be experimentally verified. So if I try to verify the de Broglie's wave equation, I have to take the assumption that there is an electron having a charge E with it, and this electron is accelerated by applying a potential of volts V. So if I apply a potential of V volts, the electron has a charge of E with it. Then at that point of time, its kinetic energy will be equal to the multiplication of the charge applied and the charge that an electron has. Also, the magnitude of kinetic energy of an electron moving with the velocity v, small v, I'll keep it as velocity. So when an electron is moving with the velocity v, at that point of time, the kinetic energy is going to be equal to half of mv square. So this is capital V here, this is small v, v square. When we combine these two equations, we see that the left hand sides are equal. That means that the right hand sides are also equal, which clearly indicates that the kinetic energy is equal to VE, and which is equal to half of mv square. If I try to calculate this velocity v here, at that point of time, what will happen is the small v square is going to be equal to twice capital V divided by m. And if I carry this square on the other side, it's going to become under root 2VE divided by m. And in this equation, if we try to put the values of V, which are obtained from the de Broglie's equation, so if we obtain the values of V from lambda is equal to h by mv, so from this equation we can know the values of V, or in other words I can say lambda into V is equal to h by m, which implies that V is equal to h by lambda m. So if I calculate the value of V from de Broglie's equation and put that value somewhere here, at that point of time the lambda is going to be equal to h by under root 2 VE by m. So I'm putting the value of this V in the equation of the de Broglie. Now in this equation, if I put the values of Max Planck's constant and the other values like mass of electron and the charge of electron and the velocity, this equation becomes equal to lambda is equal to 12.26 divided by capital V, under root capital V, this is in volts, and this equation gives us the wavelength in angstroms. So I can basically use this equation to calculate the wavelength. Now in this de Broglie's equation, if I suppose that the volts or the V is equal to 10, so if I'm applying 10 volts to an electron, then what's going to be the wavelength? So if we calculate it, we can calculate it that lambda is equal to 12.26 divided by under root 10. So under root 10 is equal to 3.162, which gives us a value of around 3.877 angstrom. That means that the wavelength is going to be equal to 3.877 angstroms. And if I vary this potential up to around 10,000 volts, from 10 to 10,000, at that point of time the equation is going to be under root 10,000, and under root of 10,000 is 100, so that means 12.26 divided by 100, and the wavelength is going to be 0.1226 angstrom. So in other words, I can say if I vary the potential from 10 to 10,000, what is going to happen, the wavelengths are going to be from 3.877 angstrom to 0.1226 angstrom. So in this range, X-rays have wavelengths. Also, in the experimental verification part, as I already mentioned, that we need to prove the de Broglie's equation in both wave terms as well as in the particle terms. So if we try to prove this equation in terms of wave nature, this experiment was done by Davidson and Germer, and they carried out this experiment in 1928. So in this experiment, wave nature of electron was confirmed experimentally. So in the right hand corner side, you can see that there's the experimental setup that was used by Davidson and Germer. So what they did is they produced a beam of electrons from a heated tungsten filament, accelerated this beam by passing it through an electric field. The accelerated beam was allowed to fall on a nickel crystal which acted as a grating. The electrons got scattered by the crystal and were received on a photographic plate on which the electrons produced diffraction rings. The rings were found to be similar to those produced by X-rays when they are diffracted by the same nickel crystal. Since X-rays have a wave character, as I already have shown in one of my previous sections, electrons should also have a wave character. So basically, this experiment done by Davidson and Germer clearly indicated that the electrons have wave nature associated with them. So in the left hand side corner, I am showing you the interference and the diffraction experiments that were done earlier by using the two slits, wherein you can see that there can be two types of interferences. It can be constructive or it can be destructive interference, and based on that we can detect the wave nature of the electrons. Secondly, we also had to prove that there is a particle nature. So the particle nature of electron becomes evident when an electron strikes a zinc sulfide screen. So if we use a zinc sulfide screen, we can clearly say that the electron has a particle nature, because in case of zinc screen, what happens is when the light falls on a zinc screen, so it leads to the formation of a localized spot. Localized spot is formed upon the incidence of light on this zinc screen. So this localized spot is also known as scintillation. The localized spot that's formed on the zinc screen, or which is called as the scintillation, this spot is totally localized. It's not spread out. So this spot is not spread. So it's not spread anywhere. It's a localized spot on the screen. Now, since the localized character is possessed only by a particle, so particle has always a localized character. So this experiment actually proved us that the electron has a particle nature, and this experiment clearly indicated that the de Broglie's wave mechanical concept, wherein we are saying that the electron acts as a wave, at the same point of time it also acts as a particle. So this was overall the experimental verification which clearly proved the de Broglie's wave mechanical concept. Moving to the fourth part of our wave mechanical concept of atom by de Broglie, wherein we'll be looking at the how Bohr's quantization of angular momentum was confirmed by de Broglie's equation. So Bohr's principle of quantization of angular momentum of a moving electron can be derived by using the de Broglie's concept of wave nature of electron. So how it is done, we'll see. According to Bohr's principle of quantization of angular momentum for any moving electron, because Bohr assumed that an electron acts as a material particle. In that case, what happens is an electron can move only in that orbit in which its angular momentum is conserved. So an electron can move in only that orbit wherein its angular momentum is conserved. So in first case, its angular momentum is going to be h by 2 pi, 1h by 2 pi. In second case, it's going to be 2h by 2 pi. Okay, because this is n is equal to 1, this is n is equal to 2, so on and so forth, the angular momentum is conserved. According to de Broglie's concept of an electron wave, we can say that an electron behaves as a standing or a stationary wave which extends around the nucleus in a circular orbit. As I am showing in the top left corner, you can see the image wherein we are showing that electrons act as waves also, and some waves are in phase and some of the waves are out of the phase. So the merging waves that are there, they show the constructive interference that is happening, while as in case of the crossing wave, you can see there is the destructive interference. In other terms, if the two ends of an electron wave meet to give us a regular series of crests and troughs, the electron wave is said to be in phase. In other words, that means there is constructive interference of an electron wave, and the electron motion has a character of standing wave or non-energy radiating motion. Whatever be the path of electron wave around the nucleus, it is necessary condition to get an electron wave in phase, so that the circumference of Bohr's orbit, which is always equal to 2 pi r, so this circumference of Bohr's orbit is always equal to 2 pi r, this is always equal to a whole number multiple of the wavelength lambda of an electron. In other words, what I mean to say is that the circumference 2 pi r of an orbit where an electron is revolving around the nucleus is always going to be equal to n lambda. That lambda is going to be equal to 2 pi r divided by n. Here n is always a whole number, which denotes the number of wavelengths that are associated with an electron wave extending around the nucleus. According to de Broglie's concept, the wavelength of an electron which behaves as a wave is always given by lambda is equal to h by mv. So this is the de Broglie's equation, and we also calculated that according to Bohr's concept, this lambda is equal to 2 pi r by n. So if I suppose this is equation first and take this equation as equation second, then what's going to happen when we compare the equation first and second? Left hand sides are equal, the right hand sides are going to be equal. That in other terms means that 2 pi r by n is going to be equal to h by mv. Or if I transpose the terms, it's going to be 2 pi r mv is going to be equal to divided by n is equal to h. Or in other words, this equation is going to be mvr, keeping mvr here, is going to be equal to h by 2 pi multiplied by n. So this equation is actually the Bohr's equation. So what we have done is that we used de Broglie's concept of wave nature of matter to derive or to reach at the conclusion that Bohr's second postulate had. That is the quantization of the angular momentum. So this is Bohr's equation. So this is how we can use de Broglie's equation to deduce the Bohr's equation of quantization of the angular momentum. This equation, which is called as Bohr's equation, clearly shows that the Bohr's assumption, namely the angular momentum of an electron, is a whole number multiple of h by 2 pi, is also confirmed only if an electron is supposed to behave as a wave as suggested by de Broglie. In other words, de Broglie's and Bohr's concept are in agreement with each other. If the circumference of the Bohr's orbit, that is 2 pi r, is bigger or smaller than n lambda, the electron wave is said to be out of phase, as shown in the top left corner, and hence the electron wave will not extend round the nucleus in circular orbits and ultimately will come out of the Bohr's orbit. That's there will be destructive interference of the waves, and that will lead to the formation of a radiation in the form of an energy. I think that pretty much covers the confirmation of Bohr's quantization of angular momentum by using the de Broglie's concept. Now, moving to the significance part of the de Broglie's concept of wave mechanical model of an atom. So the first thing is that for macroscopic objects or for large objects which are in motion, the wave character has no practical significance. So the wave character has no practical significance. And why is that? Because the wavelength that is associated with the large objects which are in motion is too small to be observed and hence cannot be measured. So this wavelength is too small and cannot be measured. Secondly, the wave character of small objects, especially the ones which are subatomic particles, when they are in motion, they have practical significance. They are also as a wave, but they have practical significance. And why is that? Because their wavelength is easily observed in the electromagnetic spectrum. The wavelengths are easily observable. Okay. So in order to visualize the wavelength that are associated with the macroscopic objects, if we suppose that there is a person who is having a 50 kg weight. So if there is a person who has around 50 kg weight, and the person is moving with a speed of around 100 km per hour, then in that case the wavelength that is going to be associated with that person is going to be lambda h by mv, which is equal to 6.626 into 10 raised power minus 34 joule second divided by 50 into 10 raised power 4 meters. 100 km is equal to 10 raised power 4 meters. Then the value of lambda, the wavelength associated with that person, is going to be around 47.52 into 10 raised power minus 38 meter. Okay, and this wavelength is almost negligible. It's very small, it's negligible, right? Now again I will take an electron, which is a very small particle, and I will again move the electron with the same speed, that's around 100 km per hour. So I am taking an electron and moving it at a speed of, at a velocity of around 100 km per hour again. And then we will calculate the wavelength and we'll see how much wavelength is associated with it. So lambda will be equal to 6.626 into 10 raised power minus 34 joule second divided by the mass of an electron, that is 9.11 into 10 raised power minus 31 into the velocity, that is 10 raised power 4 meters. So this value for an electron comes out to be equal to 2.6 into 10 raised power minus 6 meter. Now when we compare this wavelength and this wavelength, we see that this wavelength is negligible. However, this wavelength that is associated with an electron moving at the same speed of 100 km per hour, this is appreciable. That's why we say that the wavelengths that are associated with the larger objects are so small that we cannot measure them, or they are almost negligible, whereas the wavelengths that are associated with the electrons or subatomic particles or smaller particles are always almost appreciable. So from these two examples we conclude that a macroscopic object moving at the same speed as that of an electron is having de Broglie wavelength very small and negligible, whereas it's appreciable in case of an electron, which is a microscopic object. Hence, the de Broglie's relationship is valid only in case of the microscopic particles, but not to the macroscopic particles. I think that pretty much clears the de Broglie's concept of the wave mechanical model of an atom. If you like what we are doing here, and if you like our channel and the content on this channel, Bloom Buddy Educare, then kindly subscribe and share. Thank you.